Okay, good morning. So I am going to record the lecture today for those of us that couldn't make it. Please never try to kill yourself to be here. Obviously, if the weather or the buses aren't running, it'll be an excused absence. If you can call, that's fine. I'll send an email, but because we have the capabilities, I will on days where the weather's kind of iffy, I will record the lectures and I'll try to post them online, okay? So just know that obviously you'll be excused. Okay, so last time we left off talking about affinity chromatography. It's our last type of protein purification chromatography that we're going to talk about. We talked about how it has some sort of stationary phase that's specific to our protein of interest. And I left off lecture talking about immobilized metal affinity chromatography, IMAC. This is used as obviously as an affinity chromatography. So how this works is usually you have some sort of divalent metal. It's usually nickel or cobalt are the two that I've used. You can sometimes use copper. But what you do is you have that nickel supported on some sort of resin or bead. Here's your resins, usually some sort of dextrose or sucrose bead, silica bead, and then it's conjugated to these amine groups and it's coordinated. All right, so this is what your stationary phase would look like. All you need to know in regards to what your stationary phase is that it has some sort of divalent metal coordinated. Okay. And it's usually nickel or cobalt. All right? How does this interact with our protein? Well, specific amino acids can coordinate to divalent metals, specifically histidine. All right? And so remember when we talked about ways of expressing our protein, that molecular biology was one way, and so you can engineer what's known as a his tag, a polyhistidine tag. And there's usually 6 of them. So I'll just write his _6. All right, so you can engineer a polyhis tag, and that's what's shown here. 1, 2, 3, 4, 5, 6. At either the N terminus of your protein or the C terminus of your protein in order to be able to use this as a type of chromatography. All right, and people that do recombinant protein expression or expression using these molecular biology techniques, by and large, they engineer a his tag at the N terminus or the C terminus. Because affinity chromatography is so specific to your protein of interest, you usually just have to do an affinity column and some sort of size exclusion column, and you have extremely pure protein, right? This is kind of the protocol or the strategy that we use in my research laboratory, and it works really, really well. Okay? The other type of affinity chromatography that I don't want to get into too much is this antibody-antigen interaction. And we don't really talk a whole lot about antibodies, but usually they're kind of shown as a Y. So you could think of this as a primary antibody. Okay, like I said, we don't get into antibodies too much, but it's the same kind of thing. You have some sort of specific receptor. An antibody is just a type of protein, really. Some type of specific receptor that recognizes your protein of interest or your antigen. Okay? So these are the 2 types of affinity chromatography. Again, specific for your protein of interest. All right. Questions? All right, so we talked about salting out as a protein purification, but that is not column chromatography, correct? We talked about gel filtration, ion exchange chromatography, and then the last one that you'll need to know about is the affinity chromatography, okay? And if you look at the old test, you'll see a list of proteins, and I think that maybe these are on the sapling, I don't remember. And you'll have to give me a strategy for how you would separate protein 1 from 2. 3 from 4, and isolate protein X or protein 5 or whatever, all right? So you need to be familiar with how to isolate your protein of interest given a mixture of proteins, triangle, circle, square, okay? All right. So the next thing I want to talk about is this, oh man, there we go. our SDS page gels. So this stands for sodium dodecyl sulfate polyacrylamide gel electrophoresis. I don't know if I need to write that down. So SDS is just a detergent. It's found in shampoo, soap. Some people are really sensitive to it and get really irritated by it. This is called polyacrylamide. Gel electrophoresis. Okay. So polyacrylamide is just a polymer. All right, acrylamide is just some sort of polymer, and what you do is you'll initiate polymerization and essentially make your gel. All right, you can make gels of different percentage acrylamide. All right, and so different percents. Sorry, that's a different percentage of acrylamide will resolve different molecular weight proteins. Okay? So we can use that depending. Question?
What's the word before different?
Cross out. It was percent. It was percent cross out. You can resolve different molecular weight proteins. All right, so let's talk a little bit about about molecular weights of proteins. Okay, we'll talk about this in a few slides, but when I was putting this together, I probably should have inserted that here. So for proteins, we have the unit Daltons for molecular weight, and this is simply equal to grams per mole. Okay. And the way that your protein molecular weight is calculated is you look at each individual amino acid sequence and add them up, right? So we know how many carbons are in a backbone, or how many hydrogens, how many nitrogens, how many oxygens. And then depending on our side chain, we can calculate those molecular weights. So that's how the molecular weights are determined. And so for proteins, we use the molecular weight Daltons. I don't know why we do that, we just do. And so you'll see this is almost 100,000 Daltons, 66,000 Daltons, 45. And sometimes you'll see it as a kilodalton. Obviously, just move your decimal place over 3 points. So this would be 31 kilodaltons. Okay, so let's talk a little bit about the SDS page gel. This is not a purification technique. Do not get this confused with gel filtration. Okay, people do this every semester. Gel filtration is the same as size exclusion that is used to purify proteins. Okay, SDS page gel is not a purification. Once I run my part of my gel, I can't get this out and do another step. Okay, this is just an analytical method to assess purity and molecular weight of my sample. Okay, so analytical method, not purification method. They both could be considered separation techniques, but one is for sample prep, the purification. The other is just for sample characterization. Okay, so it's a very distinct difference. All right. So yeah, protein purity, protein molecular weight, and how many proteins are in my sample. So the way you look at these is going from left to right. Each one of these is a purification procedure. You have uninduced, induced. You have your cell crude lysate. Remember we talked about the first step in protein purification is to break open your cells and do a lysis. So that's, you can see how contaminated it is here. Then with each step of our protein purification, we're able to isolate our protein of interest. So we have a singular band. The molecular weight of this protein is somewhere around 45,000 Daltons or 45 kilodaltons. And this is how you would interpret this gel. Okay, you will have to interpret a gel. I think either in your homework, it was on an old quiz or test, so make sure you understand that in electrophoresis, so this is electrophoresis because electron voltage potential is put onto your gel, all right, and so this SDS gives your protein a negative charge, okay? It doesn't natively always have a negative charge on the exterior, but when you add the SDS, you get a negative charge. You put a electron potential, and the negative will go to the positive electrode, okay? This is different from gel filtration in that the smaller molecular weight compounds are at the bottom, all right? So they actually, if you want to think about it, they elute first. So on your gel, it goes from high molecular weight to low molecular weight, okay? I think there was a question last semester, what's the difference in elution between SDS page and gel filtration? Does anybody remember what molecular weight comes out in gel filtration first? I'm sorry? The larger, yeah, the bigger. The bigger the peak comes out first. Well here, the bigger peak gets, or the bigger molecular weight protein gets resolved the last, right? It gets resolved at the top of your gel. So it's actually being resolved last. The first molecular weights that are being resolved are the lower molecular weight proteins. So they're opposite of one another. And people get this confused every single semester. Okay, so try not to do that. All right, so this is used just to assess protein purity, protein molecular weight, and how many proteins are in your sample. Okay? All right, let's do a clicker question. All right, which of the following purification techniques separates proteins according to their molecular weight? Gel filtration, chromatography, SDS page, ion exchange chromatography, A and B, or all of the above? All right, you guys done? All right, what do we think? Which is a purification technique? Huh? Okay, A and C are purification techniques, but which one's only going to, all right, yes. And then now which one's going to separate based only on the molecular weight? A. About 10% of you put B. Are you awake? Please don't come to class if you don't have a pulse. Okay? And then 13% said A and B. Remember how I said everybody makes this mistake every semester and you said you're not going to have any questions? You do. Purification technique, chromatography, gel filtration, separates based on molecular weight. You can't just be a dead body in this class. You will not succeed. You have to be here and think. All right? All right. What else can we learn today, hopefully? Oh my gosh. All right. Let's talk a little bit about this other technique. So we have SDS page gel that separates based on molecular weight. Let's talk about separating based off our PIs, our isoelectric point. All right, this is called isoelectric focusing. This is another method that you can use not to determine the molecular weight of your protein, but to determine the PI. What other method did we talk about that you could use to determine a PI? Or where have you seen PIs ever in this class? Yes, wonderful. Yes. So you can perform a titration curve on your protein and determine the PI. So the other method is titration curve. Beautiful. That's exactly right. People generally don't do a titration. I don't know why. You all hate them. So they normally do this IEF, okay? It's a small gel with a different, with a gradient of different pHs. So it's decreasing. You're starting off with a pH of 9, and it goes from 9 to 3, decreasing. You load your sample at 1 point, all right, usually at the 9, and you apply, again, your protein will be negative because of the loading of the SDS that you put in it. You apply a voltage or a potential, and it begins to move, all right? Is it going to move once it reaches its PI? What is a PI, I guess? Yeah, it's where your protein's neutral. Once your protein's neutral, it's going to stop. It's not going to grow, it's not going to move with that potential anymore. So you can separate how many proteins are here. What do these spots mean? What are we doing? We're determining the PI of a protein. So I'm loading maybe a very dirty, well, two things. No, yeah, I'm loading maybe a very dirty sample, and I'm getting 5 proteins. I saw you put your hand up. You're absolutely right. 1, 2, 3, 4, 5. There's 5 different proteins with 5 different PIs on this gel. Okay? So they're going to stop moving once the pH on this membrane or this gel equals the PI of my protein, because it's going to be an overall charge of neutral. Okay.
Does the darkness of the spot correlate to like amount of protein?
Good question. Does the darkness of the spot correlate to amount of protein? It actually does. People don't normally use this to quantitate protein, but if you overload it, you'll get a big blob. And so, yes, the size of the spot or the blob does correlate with the amount that you load and the amount of protein present. Yeah, Michaela.
How do you know how long it's supposed to run for?
Good question. How do you know how long you're supposed to run it for? Let me go back 1 slide, 2 slides. You add something called a loading dye, and it's usually blue. All right, our proteins aren't blue, right? This is actually stained, but when you run your samples, you actually add something blue so that you can watch the dye front move through the gel. Once that dye front comes off the gel, you know to stop it. Yeah, great question. Otherwise, you would just keep running it and all of your stuff would come off. Okay, so PI, protein is neutral, right? We've all agreed on this. And we'll stop moving. Okay? Now let's combine our PI with our molecular weight. Okay? And this is called a 2-dimensional SDS page gel. It's 2 dimensions now because we're separating based on 2 properties. We're separating based off of our isoelectric point and our molecular weight. Okay? So this is extremely complex. And people do this normally in whole cell systems where they're looking at environmental responses or responses to drugs. So they use this a lot in drug development. Those of you that want to go to pharmacy school or medical school or go on to pharmaceutical chemistry, what you would have would be, do I still have this slide? No. What you would have would be a healthy patient and some sort of sick patient, or the sick patient and the patient dosed with the medication that's on trial or currently being administered. And you would look, each one of these spots is a protein. Look how complex these things can get, right? Because now we're dealing with a whole cell. And you sit there and look at upregulation or downregulation, okay? Between either a sick patient and a healthy patient, or the sick patient and the treated patient, okay? Okay, so let's talk about this. Combines the isoelectric focusing and is used to characterize complex protein mixtures. All right, so we have our protein sample. You will first separate based off your isoelectric point, okay? So you'll run the IEF to completion, and let's say you get, we'll just say 3 spots. 1, but you'll probably get many, many, many. Which is why you can't just run IEF to characterize, because you can't get them fully resolved. Because you may have many, many proteins at that same isoelectric point, or PI. Okay? Then you physically take this gel and put it on your SDS page gel and then separate based off molecular weight. And so now you separate based off isoelectric point from decreasing PI, high PI, low PI. Okay, we could easily put this up here, right? High, low. Then you separate based off molecular weight. Okay? Remember, high molecular weights are up here, low molecular weights are down here. Okay? So, high, low molecular weight. Yeah, Andrew.
For the IEF, do you need applied voltage?
You do.
So, if I'm understanding this correctly, your voltages are going to be, for the two different goings, they're going to be at 90 degrees.
Yeah, so you're going to run this, yeah. So this is negative. This is negative. This is positive. Right? And then that separates. Then you, yeah, you're exactly right, 90 degrees. Yep, then you take this off, run your other potential negative to positive, separate that way. Yeah. Yeah, if you just stick this in there, nothing's going to happen. You have to apply electric voltage. That's why it's an electrophoretic technique. Okay. Questions about assessing protein purity or PI? All right, let's talk a little bit about assays. So what is an assay? An assay is an experiment that quantitatively measures the amount, or this new word that we're going to talk about, activity of your protein. Those of you in lab are going to love assays. You're going to love Bradford assays, and you're going to love NADH absorbance assays, if you haven't already. They're going to whip you into shape. All right, so we're going to talk about both of these in lecture, because this is important, and this is going to correlate with enzymes when we start to talk about enzymes, but it can be any protein, all right? We're going to talk about myoglobin and hemoglobin in a few minutes, or probably Friday. And those aren't enzymes, but they are binding oxygen. So we can measure the affinity for binding oxygen by performing an assay, okay? Total activity of a protein, that's just the amount of substrate converted to product over time. So make sure you start getting this into your head. What is activity? It's the amount of substrate or reactant converted to product over a unit of time. So I produced 100 nanomoles of NADH per minute. That is my activity of gap pH. All right, so it's a rate of reaction. Miles per hour, distance per time, all right? Rates are always some unit per time. So that's the first thing we can detect, activity of our protein. The second is our total amount of protein, okay? It's not enough to just know how active my protein is. I want to know how much I have. Do I have a lot or not a lot? That's going to help me determine how much I need to make. Do I need to be doing preps every single week, or can I do a prep a month or a year and get a buttload of protein and then be able to do the biochemistry? Remember, this is just getting your starting material. Just like in organic synthesis, it's just getting your starting material so that you can undergo and do the biochemical characterization in terms of structure and function that you want to perform. This is just step one, all this work. All right, two types of assays. Let's talk first about the activity assay. You do have homework questions, and I'm pretty sure on the exam this year you will have to pick out or fill out a purification table. All right, this is all about purification. You should understand what the point of purification is. All right, the point of purification, I hope I've stressed to you, is to isolate your protein of interest. How do you do that? You do that through those different techniques that we talked about. Okay, so let's walk through this a little bit. Okay, we'll talk in a few minutes about, so this is just your volume. You're starting off with a liter and a half almost, 14,000 or 1,400 milliliters, so 1.4 liters. That's a huge amount to start off with. Then you run some sort of protein assay to determine the total amount of protein that we're going to talk about in a few minutes. All right. Then you measure the activity by some sort of analytical technique, and then you'll calculate something called the specific activity. So units of activity are usually concentration per unit of time. We've already talked about that. Can you put your phone away? So concentration per time, and specific activity is concentration per time per amount. That's bad. Amount. Okay? Something really beautiful here happens. Your activity of your protein goes down, okay? And your activity of your total protein, you're measuring total amount of protein. That should go down because your total your total volume of protein is going down, all right? So your total amount of activity is going down. But what happens is your total amount of protein, because you're isolating your protein of interest, that begins to go down as well. So what happens is your numerator gets smaller, and so you're dividing by your denominator gets smaller, right? Units per milligram, all right? And the milligram is here. So if you divide 45,000 divided by 3, you should get 15,000. So your activity, your specific activity, so your activity specific for your enzyme of interest should always be increasing with purification steps. Always. That's how you know, that's one way for you to assess that you're purifying the right protein. Your specific activity should always increase with each successive protein purification step. All right, on the homework you're going to also be asked to, all right, so specific activity, so this was calculated by dividing 45,000 divided by 3, and we got 15,000. You're also asked to calculate yield. This is determined just by dividing the protein in milligrams divided by your initial protein in milligrams. All right, so for step 5, that's a step, not stop. For step 5, we would divide our protein from step 5, 3 milligrams, and we would divide it by what we started off with, 10,000 milligrams. Okay? And then usually you times that by 100. It also asks you for the purification. Level or purity. Those are all the same thing. And you assess this by, oh crap, I don't think I wrote it down. Oh, specific activity of your protein divided by initial specific activity. Your purification level should always increase as well. Specific activity, increase. If it's not increasing, then you've got a problem, okay? Your yield is going to decrease, right, with each step, so your yield will decrease, your total protein will decrease, your specific activity and your purification level or your purity level will increase. Okay? This is just an example of kind of what you're monitoring. You're monitoring GAP-DH converting to 1,3-bisphosphoglycerate, and you're monitoring this redox reaction by UV-vis, all right, in your spectrometer. That's exactly what you're monitoring. So how much NADH is being produced over a unit of time in the presence of glyceraldehyde 3 dehydrogenase. Okay, that's exactly what you're measuring. All right, so specific activity, I think we've talked about the rate of enzyme per unit of time per milligram of total protein, measures purity. So you can measure purity by doing an activity assay or by running a gel. Okay, those are two ways that you can do it. Yes, Stephanie?
Concentration over time.
Times amount. Yeah, I just wrote it underneath it as well. Yeah. Total amount of protein. Total amount of protein. So, yeah, so for example, 45,000. What is the total amount of protein for that step in number 5? 3. That's how I got 15,000. All right, now let's talk about assessing or assaying total protein concentration. We're going to talk about 2 different ways to do this. We've kind of already talked about this when we talked about column chromatography and measuring absorbance at 280. I talked about how really tyrosine and tryptophan are 2 players at 280. And so we're going to use our equation Beer's law up there in order to quantitate our total amount of protein. This is really the easiest way to do this. All right? But to do this, you have to know your extinction coefficient, which is epsilon, right? All right. And you always want your absorbance to be, I usually say 1.2 to 0.1. This is the dynamic range or the linear range. Bless you. Okay, that means, what do I mean by a linear range if you guys have all forgotten? That means when I take my absorbance at 280, and I have an absorbance of 1, and I dilute it in half, what should my absorbance be? If I'm on a linear range. Yes, thank you. If I'm in a linear range, that means every time I double something, my absorbance should double. Every time I half something, my absorbance should half. All right? I never want to be working here at some plateau because I'm no longer at a dynamic range or the linear range. Okay? So in order to be able to use this technique, you want to be somewhere between 1.2 and 0.1, which is the dynamic range of quantitating protein by absorbance at 280 nanometers. All right. So you always have to, let's say I add my protein and I get an absorbance of something like 10. This happened to Emily yesterday. She put in her protein and she had an absorbance of 20, which is good because that means she has a bunch of protein. But I just told you that absorbance has to be between 1.2 and 0.1. So what do you think she did? She diluted it, yeah. And so you always have to go back and factor in that dilution factor. All right, let's do a clicker that does just this. You guys hate dilution factors. I'm not sure why, but I know you do. All right, determine the concentration of your protein given the following. An absorbance equals 0.41. Your molar absorptivity, which is the same as your extinction coefficient, those are synonymous, those words, is equal to 1, 2, 3, 4, 1. Inverse molar, inverse centimeters. Those are the units of molar absorptivity. All right? And then our half length is given as 1 centimeter. You had to dilute your protein 10 times. Those of you in lab know what this means, 10x or 100x. That means it's 10 times more concentrated, but it's not a concentration, right? 10 times more concentrated in order to obtain a useful measurement in this linear range. Calculate what my protein concentration would be. If you don't feel comfortable doing it in your head, don't. I diluted my protein 10 times. Okay. All right, looks like most of you are saying either A or B. Oh, it's the same thing. Yeah. That's good. This is one of these two is right. Baby steps. Let's take it. Good. I'm proud of you guys. Good. All right. All right. Are you guys all happy with your answers? No? All right. Well, let's go through it. And you guys can change your answers as we work through it. You have to know how to do this. You have to know how to do this. I know I say that and you guys just, and then you're like, oh, this isn't fair. Why did you never said that I had to know this on the test? That test was so unfair. Now I have it recorded. I will play this back to you and say, I said on February 15th, yes, that you have to know how to quantitate a protein using Beer's law, absorbance at 280, and a Bradford. Let this be noted. All right, absorbance equals epsilon path length times concentration. So we obviously all could do the math. When you do this, you get 4.39 times 10 to the negative 5. What's my unit? Yeah, beautiful. Nobody yelled at me. I'm angry at myself. Molar. It's a concentration, okay? And I got that from my molar absorptivity. I think in lab, for some reason, they give you molar absorptivity in millimolar, so your concentrations will all be in millimolar. Not my jam, but that's okay. It's always given in molar in this class. Okay. But either way, your concentration is dictated by your molar absorptivity constant. Okay, so is that my answer? A? False. Why is it not A? Yeah, there's a huge sentence here. 10 times. That means my protein, when I measure the absorbance at 280, that means that this is actually 10 times less concentrated than my actual tube of protein. Okay? And I don't care what I'm putting in the spec. I care about what's in my tube of protein. Okay? And the only reason I had to dilute it is because I was not in this dynamic range. That's the only reason. But I only really care about what's in my tube. So do I divide by 10 or multiply? Multiply. So my answer is B. 4.39 times 10 to the negative 5th molar times 10 equals 4.39 times 10 to the negative 4th molar. All right. I diluted it, so that means when I go back to find the original concentration, I have to multiply it by 10. All right, let's talk about the other method. The other method, you guys don't use this in lab for some reason. Maybe because we don't have enough specs that read 280. That's probably one. The other method is a colorimetric assay. You get these beautiful blue colors. This is called a Bradford assay. This is what you use in lab, right? And we use this in my lab. People use either method. And you should get the same answer using either method, right? The concentration of your protein is the concentration of your protein. Okay? You should. We've got some crappy Bradford in our lab that doesn't work. So, But the first thing you do is you generate a standard curve. And our protein of interest to do this is bovine serum albumin, so BSA. This is just a little tube of known protein with known concentration that you can use to make a standard curve. Okay? You did this in Gen Chem, standard curves. Many of you have done it time and time again. All right, so concentration over absorbance. Okay? You plot a standard curve. Then in here somewhere, one of these will be your protein sample. And you'll take the absorbance, right? So let's do a practice problem. I haven't done anything, but I want to make sure you guys get this. Then you take your, let's say that this one is your protein sample. And you measure it, and you get an absorbance equal to 0.411. How am I going to get the concentration? I compare it to my standard curve, and I use something very important. My equation of my line. Y is your absorbance. Sometimes it's known as optical density, but this is your absorbance. X is my concentration. I experimentally just determined that my absorbance was 0.411. I hope all of you can solve for X. Do that and tell me what it is. I didn't bring my calculator. So, what are we getting? Yeah.
Those commas like decimal places?
Yeah,
Okay.
it's a British thing. Commas are equal to decimals in Britain. What are you getting? 1.01? Okay. And for this, how would I determine what my units are? 1.01 what? I don't have an extinction coefficient now, but what do I have? I have the x-axis. I have standards. So my units are in mgs per mil. Or it might be in micromolar. It might be in micromolar or millimolar. But yeah, your units are defined now by your x-axis, not by some arbitrary extinction coefficient. You will have to do this on your exam or quiz, okay? We'll probably have a quiz over this stuff on Monday. Remember we said that. Questions? Okay. Let's continue. So we only have a few more things. We will definitely finish on Friday and hopefully get into chapter 4 a little bit on Friday. But we're going to start talking about protein structure. All right, there's a structural hierarchy that exists with proteins. Primary, secondary, tertiary, and quaternary structure. Okay? So obviously the first thing we're going to talk about a little bit is the primary structure. This is section 3.4 in your textbook. So I just said this, pure protein is step 1. You do all this work and you really haven't done anything biochemically. You haven't done any mechanism studies, you haven't done any activity assays, really studying mechanism, enzyme kinetics, things like that. You've just obtained pure protein. Now what? Now we want to do the fun stuff, the biochemistry. And this is really determining how the structure of a protein, the three-dimensional structure, dictates its chemical function. This is biochemistry at its finest. Structure affecting function, okay? And we're going to see that it does. All right, so the first is our primary structure. This is simply the protein amino acid sequence. This is where it all starts. Okay, we'll talk more about the structural hierarchy in chapter 4. CHY. Okay. So we already kind of talked about this. This is just determining my molecular weight. My molecular weight of my protein is dictated by what my primary structure is, right? If I have gly, that's going to be different than if I have serine, right? Because the R groups are different. This is going back to why do I need to know my amino acids? My amino acids are dictating my primary structure, which is dictating my protein molecular weight. Okay? This is all married together. So the size of the protein is dependent on my primary structure. Don't forget, so we're going to determine the molecular weight of, what is this tripeptide? Alanine, tryptophan, not phenylalanine, proline. Phenylalanine is F. Yes, I know. It's good. It's good to keep practicing. All right, don't forget when I form this, that now I've undergone this condensation reaction, so I lost those waters. All right, so this table already takes that into consideration. All right, and this will be the table I will give you. Please don't memorize the molecular weights of your protein or of your amino acids. I'm not that mean. I'm pretty mean, but not that mean. All right, this will be provided for you. Okay, the structures may not be there, but the molecular weights will be there. The three letter code and the 1 letter code may not be there.
So if we're assembling a whole bunch of amino acids, does that mean that we should add 1 water into this since those fumes are not?
Great question. Absolutely. Andrew said, okay, well, you just told me that these have already subtracted 18, but what about my N terminus and what about my C terminus? There should still be that water there. Do I have to add 18? Absolutely. Absolutely. Let's do this. Or do we have time? Yeah, we have 1 minute. All right, alanine. 71. Tryptophan. And I'm just using the average. Proline. And then Andrew, 18. Where does this come from? My water. N term and C term. And I got 366 Daltons, but please check my math. All right, remember the Dalton is the same as grams per mole. If I sit there and add 12 plus 12 plus 12, 12, add all this together, I should get 113. Alex.
You have to put Dalton to use acceptable for grams per mole.
I want you to put Dalton. Thank you, very good question. Is it acceptable to put grams per mole, or do you want Dalton? I want Dalton or kilodalton, and I'll ask you to give it in either way. Have a nice day. Please don't give up online. If you did not get your quiz for chapter 3 amino acids, a fair amount of you did not, please come get them. Here's your quizzes. 97. Hold on, I think I wrote down the wrong.